So today we'll look at transverse and longitudinal waves. Firstly, I want to talk about what a wave actually is. So a wave is just a way of transferring energy without actually transferring matter. Okay, so for example, if you take a tennis ball and you throw it into a pond, then that tennis ball is going to cause ripples. Those are waves moving through the water, but the tennis ball itself is going to stay in the middle of the water. Likewise, the water itself isn't going to be moving away from the tennis ball. Okay, it's just the waves that are moving away. All of the matter just stays in place. It just oscillates up and down. It goes up and down. So we'll look at transverse and longitudinal waves. Before we look at those, we'll just talk about some of the properties of waves. Okay, so the wave I've drawn on the screen is actually an example of a transverse wave. Okay, transverse waves oscillate up and down, and again we'll look at this in more detail a bit later on in the video. But they've got various properties. Okay, so firstly I'm just going to point out some things. The peak, these bits at the top here, these are called peaks. Okay, sometimes they're called crests. Okay, and then we've got the bottom bits down here, these are called troughs. Okay, so you've got peaks and you've got troughs. Now the wave itself is going up and then down again, okay, and it's doing so about a central position here. So this line in the middle is our central undisturbed position, and the wave itself, the molecules are displaced up and down about this central point. Okay, so this is what we've got. So we've got peaks, which is the point of maximum displacement upwards. We've got troughs, points of maximum displacement downwards. Okay, now we've also got wavelengths. Now the wavelength of a wave is just the distance between 2 points, two similar points on a wave. Okay, so for example, between 2 peaks here. So this is the wavelength. That's the wavelength, the distance between 2 peaks. You could also have it as 2 similar points as 2 troughs, so you could have the wavelength there. You could have the wavelength as from this point here to this point here. You could also have the wavelength from this point here to this point here. It doesn't really matter. It's just the wavelength is just how long, or how the distance, the length of one complete cycle of the wave. Okay, so one complete cycle, where this is one complete cycle, that's a second complete cycle, and then that's just like sum of a cycle. Okay. What else have we got? We've got amplitude. Let's look at amplitude. Amplitude is just the height of the wave. Okay, so that's the height from the central undisturbed position. That's the amplitude. You could also say that that's the amplitude there. And we also need to look at frequency. So what is the frequency of a wave? So the frequency of a wave is just how many times per second it makes one complete cycle, or how many oscillations every second. So one oscillation is one complete cycle. How many complete cycles it makes every second, that is the frequency. You can also think about it as how many full waves travel through a certain point every second as well. Okay, so how many complete waves pass through a certain point every second. This is measured in a unit called hertz, Hz. Okay, hertz is just another way of saying per second. So if you've got 500 waves passing through a certain point every second, then that wave has got a frequency of 500 hertz. We also need to talk about the period of the wave. So the period of the wave is just how long it takes to make one oscillation, or how long it takes for a whole wave to pass through a certain point. So how long it takes for the wave to make one complete oscillation. And remember, one oscillation is just one cycle of the wave. Okay, so one oscillation would be that. Okay, that's one oscillation. This is measured in seconds. You can relate the two together, period and frequency. So the period of the wave, if you just take 1 second and you divide it by the frequency, you get that. You get 1 over f. Okay, and before we move on and look at transverse and longitudinal waves in more detail, and we look at some examples of that, I just want to introduce you to the wave equation. So waves have got a certain wave speed. Okay, so how fast they travel, that's v. We're going to represent that with v. That's equal to the frequency of the wave times by the wavelength, and we're going to represent wavelength with this Greek letter lambda. Okay, so we've got wave speed in meters per second. We've got frequency, and we've got wavelength in meters. Okay, frequency in hertz. Okay, right, let's have a look at transverse and longitudinal waves in more detail. Okay, so here is a simulation then of longitudinal and transverse waves. So we'll start by looking at transverse waves. So the one at the bottom, the blue wave, is our transverse wave. Okay, notice the way it's oscillating. It oscillates up and down. It oscillates perpendicular to its direction of energy transfer. Its direction of energy transfer is forwards, and it's oscillating up and down. It's oscillating perpendicular to that, and that's what a transverse wave is. An example of a transverse wave is electromagnetic waves. So electromagnetic waves, light is an example of an electromagnetic wave. We'll look at other types of electromagnetic waves in a future video. Ripples in water, so waves in water, if you remember the tennis ball example I used, those ripples, those oscillate up and down in relation to the direction of energy transfer. They are an example of a transverse wave. A wave on a string, if you take a string and you just shake it up and down, then that's going to cause a transverse wave to move along it. The one at the top is a longitudinal wave. Okay, so the energy, so notice that, that it's actually compressions that are moving down through the medium. It's not moving up and down, it's compression, so it's moving forwards and backwards. It's oscillating forwards and backwards in relation to its direction of energy transfer. Now you've got regions of compression where there are a lot of these red lines pushed together. Areas of compression, and then you've got stretched out areas. These are areas of rarefactions. Okay, these stretched out bits moving down as well. Okay, and this is how a longitudinal wave moves. Examples include sound waves. Yeah, sound waves travel as compressions in the air. That's a longitudinal wave. Ultrasound, which is just sound waves but too high pitched for us to hear. We'll look at that in a later video as well. And also certain types of seismic waves. Seismic waves like earthquake waves, things like that, move in longitudinal waves. Some of them don't, but some of them do. Okay, we'll talk again. That's for another video. So this is a longitudinal wave. Compressions moving through the material. Okay. Right, I will see you in the next video.